Welcome to Summarize Science, where we break down the latest breakthroughs in the world of high-tech research. Building a massive quantum computer is currently a giant engineering puzzle, mostly because today's qubits require a wiring nightmare of bulky microwave components and amplifiers. These parts take up a lot of space and create heat, which is a major problem for systems that need to stay near absolute zero. Researchers have explored a clever new way to solve this using something called fluxons. A fluxon is essentially a solitary wave of magnetic energy that travels like a particle down a specialized wire called a Josephson transmission line. Instead of using complex microwave pulses, this new scheme uses the timing of these magnetic waves to figure out what a qubit is doing. On page 2, we can see the layout of the transmission line, which is made of a series of tiny superconducting junctions. Each cell in this line is designed to facilitate the movement of those magnetic pulses without losing energy. The researchers focused on a specific type of qubit called a transmon, which is shown here connected to the transmission line via a small capacitor. As a fluxon travels past the transon, the interaction between them causes a tiny change in the wave's velocity. If the qubit is in one state, it might accelerate the fluxon, while another state would cause it to decelerate. By measuring the time it takes for the fluxon to reach the end of the wire, the researchers can read the qubit's quantum state without direct, noisy contact. This graph shows the time delay and how it changes based on how fast the magnetic pulse was moving when it started. One of the most interesting findings is that these pulses don't get pinned or stuck to the qubit, which has been a failure point for previous similar ideas. Because the pulse keeps moving, the readout is much more reliable and produces very little error. Furthermore, this method is non-destructive, meaning it doesn't accidentally change the qubit state while trying to read it. Looking at these snapshots, you can see how the pulses stay sharp and distinct even as they are accelerated by the circuit. This technology could allow scientists to replace big, power-hungry microwave equipment with tiny digital circuits that work right inside the cryogenic refrigerator. Another massive benefit of this specific wire design is that it acts as a natural filter. Quantum states are incredibly fragile and can be destroyed by any stray noise from the environment. This transmission line has what scientists call a spectral gap, which blocks out noise that would otherwise interfere with the qubit. This means the hardware doing the reading is also serving as a protective shield for the computer's memory. By combining readout and protection into one small wire, the overall footprint of the quantum processor shrinks significantly. In the end, these researchers demonstrated that magnetic time delays are a feasible way to simplify quantum computers. To recap, fluxon readout avoids the need for bulky microwave wiring, prevents magnetic sticking, and protects qubits from environmental noise. This could lead to a future where we can fit thousands or even millions of qubits on a single chip without it overheating or becoming a tangled mess of wires. This approach moves us one step closer to a truly scalable quantum classical architecture. If we can master these magnetic ripples, the dream of a large-scale, functional quantum computer might be much closer than we think. Thanks for watching Summarize Science, and stay tuned for more breakthroughs that are shaping the future of technology.